Hi, in this second example on finding the maximum and minimum application problem, this time we're going to take a look at finding the maximum volume of a container. Now, as it says here, we start with a rectangular piece of metal 8 by 5 and a square of side length X is cut from each corner, and the resulting piece of metal is then folded and welded to form an open rectangular box. So as it shows there, it's 8 by 5. So if we take X out of each end, that means that this length down here then is 5 minus 2X, which becomes the width. From there to there is going to be 8 minus 2X, which becomes the length. And of course, the dotted bit here, when it folds up, becomes the height. Now, so this question is going to ask us to do 5 things. Firstly, to express the volume in terms of X, and we need to show it's equal to that. We need to state the domain for which this problem would be valid for, and then we have to find the value of X such that the box has a maximum volume, and then state what that volume is and the dimensions, and finally sketch the graph. Okay, so let's start with A. Now we know that the volume of a rectangular container is length by width by height. So if we put that together as such, here we got length by width by height. And if we then expand that, so I've expanded the two brackets, and then multiply through by X, we get V equal to 4X cubed minus 26X squared plus 40X, which is what we had to show. Now, just on the right here, we see what the graph of that looks like. So we can see that obviously if X is less than 0, we have a negative volume. So that's going to be one constraint of the X, that it has to be a positive value. And we can see that it raises to a maximum value at some point. It's back to 0, and then we have negative volume again before it becomes positive. Now, let's look at the dimensions of the box up here. Now, if this is going to be a positive volume, we need to have that the product of all three things has to be positive. So certainly we can see from the graph that X has to be greater than 0. Now, we also need this part here to be greater than 0. So solving that would mean that X has to be less than 4. And the second part needs to be positive, which means X needs to be less than 5.5. Now, if we take the first value, let's say we take X equal to 3, substituting it up here, we've got 3, which is positive, but then 5 minus 2, 3 is 6, 5 minus 6 is equal to negative 1. So although that value works for the first bracket, it doesn't work for the second bracket, which means then that we have to look at the second value here. So our domain has to work for both brackets. So if we look at this one, X being less than 5.5, let's say we take X equal to 2. X is 2, so that's positive. 5 minus 4 is 1, that's positive. And 8 minus 4 is positive. So therefore, X is going to be between 0 and 5 on 2, which is basically what the graph is showing. Here's 0 here, and that point then would be 5 on 2, or 2.5. So the domain then is X has to be between 5 and 2.5. So that answers part C. Now part D wants to know, when does the maximum occur? So here we have our expression for volume expanded up here. So if we take the derivative of that, which will give us 12x squared minus 52x plus 40. Now, stationary points occur when the derivative is 0. So we can see at this point here, there's a stationary point, and at this point down here, there's a stationary point. This is the one we're interested in here because at this point, the volume has a positive amount. Here, it's suggesting the volume is negative, which is impossible. So we're only interested in this part of the curve here, above the x-axis. And of course, this point down here, taking x greater than, say, what's that, 1, 2, 3, greater than 4. Let's say we took 5. 8 minus 10 is negative. Although they would give you two negatives, it'd be impossible to sort of, well, you can see here you can't take a value x 5 because you've only got 5 to start with. So if you take 5 out of one end, you've got nothing to take out of the other end. So that's impossible to have. So x has got to be between, as we said, between 0 and 2.5. So that factorises, and we want to know when that's equal to 0. So solving that suggests then that there are two values, x equal to 1 and 10 over 3. The x equal to 1 falls within our domain, which means it's this particular value up here. And 10 over 3, which would be 3 1/3, which would be this point over here, which gives us certainly gives us a stationary point, but it's indicating a minimum volume, which is negative, and it's outside the domain, which is between 0 and 2.5. So this one's not valid for our domain. So we take then that the size of the piece to be cut out of each end is x equal to 1. So if x is equal to 1, when we substitute 1 back into our equation here, you're going to get, that'd be 6 times 3 is 18, by 1 is 18. So the maximum volume then is 18. And the dimensions of the box then are going to be 6 by 3, because we take a metre out of each end, leaves us with 6. A metre out of the width of each end is going to leave us with 3. So the dimensions of the box then are 6 by 3 by 1 metre high, gives us 18 cubic metres. We've already discussed the domain of being between 0 and 5.5. We don't include the endpoints because at either value that would give us 0 volume. So if x is 0, that would give us 0 volume, which is a useless box. It doesn't hold anything. And if x is 5 on 2, that would give you 5 minus 5 there. Again, volume is 0. So we have to be greater than 0 but less than 2.5 to have a box that's got a realistic volume in it. So here we are with just that part which has been expanded. So we've drawn it for the required domain. We've got the open circles here showing that it doesn't exist at x equal to 0 and x equal to 2.5. And here's the maximum occurring 18 cubic metres when the x value was 1.